Everyone, this is recorded as usual, so if you would like to rewatch it or check out the recording or send it to anyone else, we'll share that on Slack after the call. So welcome everyone to today's Research Connection speaker series. The research series highlights the relationships being built across our teams and the exciting work that's happening in the industries that Autodesk serves. If you have a speaker that you think the research community should hear from, I'll post a link in the chat for you to fill out our Research Connection speaker series form, and then the community team will reach out to you for next steps. And then I'm very excited for our talk today, situationally aware robots for construction applications. But first, I would like to invite Pan Zhang to introduce our speakers. So Pan, I'll hand it off to you.
Okay, thanks everybody for joining. So today we have Dr. Jose and Dr. Hriday they're from University of Luxembourg about their interesting research. The research areas they have done some amazing research works for aerial robots, specifically for simultaneous localization and mapping, SLAM, and visual SLAM, and collision avoidance, and semantic awareness, and also motion planning with movable objects. And they've incorporated methods from situational graph for indoor scenarios and collision avoidance and semantic awareness, and lots of motion planning and techniques. So I think that's very interesting for us for this talk. So I'll just give away this to our two research scientists here.
Thank you very much, Pan. Are you able to hear me properly?
Sounds good.
Yep.
Yes.
Yeah, all good. Okay. So thank you for the introduction. On behalf of Jose Luis, my colleague, I will present today's presentation. I think there was Alex, I saw, had a question. If there was a mistake, or should I continue?
No, it was just a thumbs up that I could hear you.
Okay, perfect. Thank you. Okay, so I will just share my screen so we can get going with the presentation. Are you all able to see my screen? Yes, okay. So, yeah, as Pan introduced us, we are from the University of Luxembourg. I'm Dr. Hriday Bavle. I'm a postdoctoral research associate at the University of Luxembourg. You have my colleague here as well, Dr. Luis Sanchez-Lopez. He is a research scientist at the university as well. And our supervisor, he couldn't make it today, Professor Holger Voss. He's supervising the entire our group. So let's say Pan already introduced the talk. It's situationally aware mobile robots for construction applications. So before diving into the topic, I would just give a bit of a background of what the university is comprised of and where it is and where is Luxembourg, because Luxembourg, a few years ago, even I did not know where it was. It's a really small country. And it's the only university that we have in the country, which is the University of Luxembourg. And it's quite young. It was established in 2003. As I mentioned before, our research group is the Automation and Robotics Research Group from the Research Center, which we call the SMP, Interdisciplinary Center for Security, Reliability, and Trust, which is a part of the University of Luxembourg. Our head is Professor Holger Voss. Then at the next level is Dr. Jose Luis Sanchez-Lopez. So at our group, we focus on different research lines. Mainly, the first one is the situational awareness for mobile robots. Then we have other research lines like optimization for path planning and automation. Then we have also advanced control and actuation. And we have these research lines so that we can then apply it to different application areas. So robotics for constructions is one of the application area. Then we have aerial robotics and aerial manipulation, Industry 4.0, autonomous driving, and some space applications as well. And then we have some labs at the uni where we can do some tests internally in the labs. So you can see some in the pictures here. There are some, the aerial robotics lab at the rightmost part, where we have the setup with the Viken cameras to get, let's say, the real-time post acquisition of the robots, and we can do really complex tests in the lab. We have an autonomous car where we can do our tests, some social robots, as well as the other robots like the Spot and the Unitree Go robots, as well as some manipulators. So I will, with this background, I would like to then present today's agenda of what I will be presenting. Firstly, I would just present briefly of what our robotic solution for construction looks like, how we have developed it, and for what robots we have developed it. And I would then dive a bit into what our research looks like, or how are we designing or developing our research. And finally, I would just explain a bit about the industry partnerships that we have and the funding sources. So how are we, or what is the robotic software solution that we are providing? We have a complete software framework which enables the robot to work autonomously or navigate autonomously on construction sites. We heavily use robot operating systems, ROS, which is a very common tool used by the robotics community. So all our robots are powered by ROS. And yes, like most of the robots, we have Wi-Fi connectivity, and also we have tested it with 5G connectivity as well. So as you can see in the figure on the right, there are like multiple platforms that we have been working with. Maybe started with the Boston Dynamics Spot, which is now we tested it fully functional on many of the construction sites. Then we acquired a new robot as well, the small gray robot on the right of the picture. It's the Unitree Go 1 robot. It's smaller and easier to test with, I would say. Then we are also, let's say, looking into other robotic platforms like the Anibotics, a Switzerland company, as well as Legged robot. We use then different onboard sensors to give this situational awareness to the robots. So some of the sensors that we use are LIDARs, which are 3D LIDARs mainly, RGBD sensors, which is like the cameras, which also give us the depth information of the environment, normal RGB cameras. And we use like different onboard computers, which are like all the Intel NUC or the NVIDIA computers. The autonomous capabilities that we are providing to the robot are things like mission scheduling, where a user can give different waypoints, schedule a mission and give different waypoints on a construction site. The robots then have a reactive obstacle avoidance capability, so that then it can follow the path. And the main component is the situational awareness, which I will be presenting in the next slides. And we believe that situational awareness is one of the main components over here, because the more aware the robot is about its environment, the better decisions it can take while planning a path or executing a mission. So with this, I would then highlight a bit about our research, starting with the LIDAR-based S-graphs. So by S-graphs, the full form of S-graphs is situational graphs, because for us, we wanted to develop graphs which gave robot more awareness of its situation. So situational graph, the idea behind the situational graph is that it's a complete graph which gives a better understanding of the situation to the robot. So it's a LIDAR-based graph optimization algorithm which simultaneously builds a map of the environment while it's also getting or giving the robot the estimate of where it is in the environment. So as you can see on the figure on the right, can you just give me a thumbs up if you can see the cursor? Yeah, here. Okay. So over here you can see in the figure, this is one example of S-graphs built on an actual construction site. So we divided. The idea is behind this S-graphs is to tightly couple geometric, semantic, but also relational abstractions that could be present in the environment. One of the typical examples where we applied it to, which was the construction site, and the common semantic elements over here were wall surfaces, then rooms, as well as floor levels. So over here on the construction side, the bottommost part, if you can see, is the 3D mesh or the 3D point cloud of the environment, which was generated as the robot navigated in the environment. But while it navigated, it was generating keyframes. Over here, keyframes are basically robot positions, which are captured at different time and distance intervals. So you see like the spheres, which are like positions of the robot as it navigates in the environment. So as it navigates in the environment, it observes some of the landmarks, which in our case are the walls. So when it observes walls, you see over here are the different colors that we depict them, and they are like the walls which our robot observes using the LIDAR. And over here, our contribution, our novelty was how we could encompass all these walls into rooms, which are like newer entities that we are proposing. Because when you have an abstraction, when you have a wall as a semantic abstraction, you can then encompass them efficiently in rooms. In our case, we use wall or rooms which have 4 walls either or 2 walls. So 2 walls could be like corridors or long hallways. And then each of those rooms then could be encompassed on different floor levels. So then you could have multiple floor levels which encompass the different rooms at that level. Then each room encompasses different walls at that level and respectively as going down. And the robot does it while it navigates real time in the environment. So this is in the video on the left, you can see an example of how the robot navigates while it's generating extracting first the walls and then the rooms and the floors. The video was accelerated 10 times, but it was navigated like at a normal speed. It was using a spot robot. So this is an example on another construction site where you can see that as the robot navigates, it creates this graph, but thanks to this graph, it's also creating a really accurate map of the environment. So then we can not only obtain higher level representations of our environment, but at the same time, we are improving the accuracy of where the robot is in the environment and also the accuracy of the 3D map that we generate for the environment. So one of the ongoing research that we are adding in this S-Graphs is basically to add now test it on multiple floor levels, test staircases, windows, also adding machine learning capabilities for abstracting or better abstracting the scene graph, or let's say the graph, or better understanding the graph that we are extracting, and also optimizing it at hierarchical level. So since we have a hierarchy of layers, like we have rooms, floors, so we could use this or exploit this hierarchy to optimize better and faster. So what are the expected outcomes from this? That we believe that this will help in making better digital twins of the environment, but also it improves the overall understanding of the robot and its localization and mapping accuracy as well. So with this, I finished the S-Graphs part, and then I would like to show you how we could exploit these S-Graphs using the pre-existing knowledge that we can acquire from BIM or the Revit models to then localize or use this info prior to exploring a construction site, so that then the robot doesn't need to explore the entire construction site, but use already pre-existing knowledge from the BIM and then localize itself within the environment. So we call this work as informed S-Graphs. It's because we are augmenting or informing the S-Graphs with the knowledge from architectural graphs, which is the knowledge that we extract from the BIM. We call it A-Graph. So you can see over here on the figure on right, the robot, as it navigates the environment, generates an S-Graph, which has all the representations that I mentioned before, that it has these keyframes, these walls, rooms, and floors. And we can extract the same information from an A-Graph, that is basically we can read now the Revit plans and we can get all these connections which are present. So in Revit, we have walls those are, we know how are they connected to rooms. We know how rooms are connected using doorways, and also we know which rooms are on the floor level. So if you can have this prior knowledge, as the robot starts exploring the environment, we proposed a matching algorithm to know which room exactly matches which one in the A-graph, to then merge both the information, and then you obtain an IS graph, which is an augmented S-graph with the prior information coming from the BIM. So an example video of how this looks like, this is a simulated environment. I would just like to go a bit slower on this video here. So as the robot at the beginning doesn't have any knowledge of where it is, what it only knows, it has an A graph, but at the beginning it doesn't know where it is inside this A graph, which is, let's say, inside this BIM. So it starts randomly at any position. It starts extracting the S graph, and it starts building this higher level knowledge. And while it's doing it, we are continuously trying to match which of the rooms which of the rooms match with the rooms within the A graph. And once it finally finds a match, it then merges both of them together. And then now the robot can already use some pre-existing knowledge which was there in BIM, and which the robot hadn't explored. So imagine this as an example where the robot starts in room 1. It already knows that I am in room 1, and the BIM has 10 rooms. The robot doesn't need to explore 10 rooms. Once it knows where it is in the BIM, it can then navigate efficiently to the 10th room, because it knows this from the BIM. This was in simulator, and similar results. I think this is the only result. What do we expect? What we also see this research as quite powerful. We actually got a best paper award at a recent conference, a robotic conference that we attended for this work that we presented. So we believe that this work has a lot of potential also. So we are trying to focus on, we are focusing on adding more abstractions that we can extract from Revit, like staircases, windows. And then also another powerful thing over here to add would be to compute deviations, because this would be a very powerful tool that we can compute deviations that could be present in the actual build plans when comparing it to the BIM. So the expected results are to increase the accuracy of the robot within a construction site, while simultaneously knowing the deviations, and you also generating better digital twins of the construction site. So with this, I finished the part where we used S graphs and the IS graphs, and the main or the sensors that were used in these works were 3D LIDARs. But vision sensor, that is cameras, are also powerful, and we would like to exploit those as well. So we started some works in this direction as well, where we try to exploit S graphs using just single cameras and Arupa markers. Arupa markers over here, just to give you a context of what is an Arupa marker, it's like a fiducial marker. It's like a QR code that we use. But these are more fiducial markers that the robot, they give a relative position of the robot, relative position information to the robot. So using a setup like single camera and these fiducial markers set up in the environment, we can generate also similar structures like S-graph for a given environment. So over here you can see this was done using a single camera. That's why the points or the map that you see is a bit sparse compared to the 3D map that a LiDAR generates, but we can obtain similar representations like the rooms and the corridors. One of the things over here, what we are exploiting as well, is that no one likes to pollute their environment with with these markers, because the environment basically looks ugly and you don't want to paste too many markers in the environment. So we are collaborating also with the physics department at the uni, and they are generating a kind of invisible markers to the human eye. So over here you can see an example. If you put it on a white surface, it's practically invisible, but using a suitable camera setup, the robot can detect it. So then we can replace these visible markers with these invisible markers, and this has a potential to be put on construction sites as well. So over here in the video, you can see as over here is just a handheld camera that we are moving in the environment. So as it's moving, over here on the top layer are these the markers. Over here are these fiducial markers that are being detected and being mapped along with the points. And as it does it, it also generates the rooms in the environment. So we would like to extend this work using, let's say, adding features like inertial sensors as well, like use it using more RGBD, like cameras which have depth information, then use machine learning techniques also to improve the image segmentation parts, and also then finally integrate the invisible markers that I previously showed into the complete framework, so that then we don't need to pollute the environment with actual visible fiducial markers. So we tested this algorithm, and what we expect also with the future results are the improvement in the localization and mapping accuracy, and also the better performance while reducing the visual pollution of the environment. So now the next two slides, what I will present are really very recent works. They are we have just started to explore them since the past 1 or 2 months, but the idea is quite powerful. What I will present behind this. So since we have a graph-based structure which gives us, let's say, a lot of semantic entities, but also ordered them in a hierarchical manner, we could exploit this and use multiple robots to build this information and then merge this information efficiently. So by this, what I mean is when you want to explore a really large construction sites, you can do it using 2 robots, which would be way faster. So S-Graphs permits us, the way it's organized, it permits us to do it using multiple robots. To give you an example, over here, agent 1 sees a blue graph, and the agent, let's say 2 in this case, sees the red one. And if we are able to match the rooms, or if the agents know that if agent 2 knows that now I'm seeing the room that agent 1 has visited, I can merge all the information from agent 1, all the information coming from agent 1 to my graph as well. In this case, both the agents are working in a distributed manner and communicating continuously with each other. So this is again on a real construction site where we did initial tests, where the robot on the left, here it is right now, but it started here at this part, and it started exploring all this area. And this robot, the second one, hasn't explored this part of the map yet. But since it already knew, because they had a common room, that is this room in the middle, that was the one that they explored, the same room. The robot 2 has elements in the map which were only seen by robot 1. So you could efficiently use S-Graphs over here to do multi-robot communication and multi-robot graphs to create or explore construction sites really faster. And then, of course, since this graph is really a higher level graph, giving you a lot of semantic entities, you can even plan better. So like us human beings, we plan when we need to go from room 1, or I need to go from my room to my colleague's room. I know how is the path first, at the room level. So I know that if I need to go from my room to my colleague's room, I need to pass the colleague X's room first, and then then I can go to my colleague's room. So it's the same concept we can apply while if we generate S-graphs, which gives us this rich semantic information, we could even plan better. So for giving you an example, over here is this is a simulated experiment where we have the rooms which were generated by the S-graphs, and these are the doorways which connect the different rooms. So now the goal is this place for the robot, and this is the start place. So over here, as you see, when you execute, it knows the path, the initial path, using the rooms. Using the rooms and the doorways it needs to take in order to go from the start to the goal. So this allows you to plan really, really fast. And then once you have a rough plan at a semantic level, which is in this case rooms, you can then do geometric level planning where you can avoid then obstacles at wherever a robot sees an obstacle, it avoids it while it tries to reach the room. So if I continue this video further, you will see now we change the start position to a different room, and yeah, now it gets an updated plan, which is in green, that it needs to go from this room to this doorway, or the opposite. The start is here, so it's from this room to this doorway, and this doorway to this goal. So this is also a quite recent work that we have started exploring. So the results are also quite preliminary, but we also again see quite a bit of potential here. So we would continue exploring this research as well. So with this, I finished mostly the research part that we are doing with the situational awareness for mobile robots, and mostly applied to the construction side. And I would just give a brief introduction to the funding sources that we have and the industry partners that allow us to apply our research to actual industry. So we have a lot of funding from Luxembourg, from the public agencies of Luxembourg. So the Luxembourg Public Funding Agency, we have research projects that allow us, we have funding for our research projects that allow us to do pure research. But then we also have industry partners. One example is Tugalux, which is a local partner here, a construction company, where we deploy our robots and we test our research on many of their construction sites. We were in contact with the HPP architects. Also, they are also in the Autodesk network for a potential partnership. We have the Air Lab here from Luxembourg, as well as Spacetime, a technology company for construction applications as well, where we are looking into partnerships for applying our research to actual industry. And as you know, that we are also a part of the Autodesk network, that we are always able to get in touch with industry experts. And with that, I conclude my talk for today. And we are always looking for partners, because personally we believe that applying a research is always powerful when you apply to an actual industry. So it's always interesting to collaborate with industry partners. With this, I would conclude my presentation for today, and I would give more time for discussions if you have any.
Amazing. Thank you so much. Really nice job. And I see some applause in the audience. Is there any questions from our audience? And this can be a conversation, so feel free to come off mute, and you can ask Hriday or Jose directly. Daniel, I see you come on camera. Working on mute. There you are.
Yep. This is really fascinating stuff. Thank you for bringing it and sharing the information.
Thank you.
I had two questions, one organizational and one technical. First one, when you are, you said you work with construction companies to test the new technology on site, or to not even test it, but to like experiment and run it and see what the environment's all about. What's the arrangement with the construction companies to be able to do that? And the reason I ask is that we found that the on-site teams, a project manager and otherwise, on a construction site are so busy that they don't want anything on the job site that's going to interfere with their ability to deploy the project. So how are you arranging that?
Do you want to answer this, Jose Luis?
Yeah, I can maybe answer. So first of all, hello everyone. I was muted before, but I can answer. So it was actually one of these construction companies, Stugalux. They bought one of these Boston Dynamics spots because they wanted to, robotize their processes, but they got a little, let's say, disappointed. Because they thought it was going to be press a button and then the robot was going to go on its own. And then, yeah, that was not the case. So they came to us and they said, oh, guys, I know you are robot experts. So could you please help us to robotize these platforms? So we only press a button. So it was actually their initiative. So this is why it has been super easy, because it's their interest to do it.
Okay, so you haven't gone out to other companies to say, hey guys, here's this new idea, we'd like to test it with you.
Yeah, so that was the first one, and then the rest, for example, HPP, that came after, because once you are able to show that you are really working in real construction sites, then it's easier for them to also want to engage.
Okay.
One thing I've noticed with a lot of our teams is it's once you have a connection at like a big construction DC, it's easier to get like a pilot project than it is to sell and become a daily part of the construction life cycle. So like breaking into commercialization is still a struggle, but getting research pilots seems possible. I mean, that's just what I've noticed.
Yes, actually, indeed, that's right. So then the challenge we are now facing is that, yeah, we are a research institute. We are not a technological company. So we are able to prove the technology, but we are not able to commercialize it. So actually, we are now looking for a technological partner that is willing to take over our research solution and, research, ongoing research, and make it commercial. You have to raise the technological readiness levels, so it can be a product that a company can directly use.
Excellent, thanks. So the other quick technical question, when you come into a room and you're looking around and you're matching that room with the architectural graphs, right, to identify where you are, how much you're also at the same time, you walk in and you're noticing that there are variations between what was planned and how it's actually been built, right? How much of a difference is there before it throws off your localization scheme, where it's so different that you're like, I don't even recognize this, or the robot says, I don't even recognize this room. Yeah. At what level of variation does that break?
Yeah, this is a great question.
I thought but I don't think we have numbers, specific numbers for that, because this is like the research we are diving into now. So we plan to get the exact numbers, let's say, of, the localization breaks at 50 centimeters of an error when we have the as built and as planned, because in the work that I just presented now, it was assumed that we don't have deviations. Because the math, if like you said, if there is one wall off, the worst case can be that there is no wall there. What would do is not detect a room, and this would basically lead to it not matching it with any of the rooms in the A-Graph. So it would take then more time for it to localize inside the environment. and from our test minimum that we found, you need at least 2 rooms, which are not really similar. More or less similar works, but yeah, you need a bit of this symmetry in order to then match it with the A-graph in this present work.
You allow me to complement. So the hypothesis of the work that Hriday presented was that, yeah, there are no deviations, as he explained. And now we are exploring how we can also incorporate the deviations, so potential deviations between the as-built and as-planned, and actually already provide this information to the user, to the end user, not only for the localization of the robot itself to be able to localize, but also to already give an estimation of this deviation error. But this will also be heavily influenced by the sensors we have on board. So the sensors we are using, Hriday explained, so we are using low resolution LIDARs. So of course, we cannot compare with high resolution LIDARs because they are mostly used for the robot navigation, not for the measurement of the deviation themselves. But still, we are planning to be able to provide already an indication of a deviation. Does this answer the question?
Yep. Thanks.
Thank you.
Thanks, Daniel. And does the localization data always take precedence over the BIM model, or the hard model?
Can you repeat your question? Like, I didn't get it.
Yeah, does the localization data that the robot's collecting always take precedence over the pre-built model?
So you mean like if the localization data, like it's more, we weigh it more than the BIM data, or this is what you mean? Or I'm not sure how to answer this. Like, because in this case, what we assume in here is like the BIM is the most accurate.
Mm-hmm.
So in this case, like when we say that, okay, now you have a match with room X, which is in that BIM, you have to the actual detected room has to coincide with the one in the BIM. So we right in this work we say that, yeah, BIM is accurate.
Okay.
What is so we then we are assuming here that the information from the BIM is completely accurate, completely true.
Yes, but anyways, what the algorithm keeps on doing is that it could continue mapping things that are not in BIM.
Mm-hmm.
Okay, so if, for example, there is a wall that is not in BIM, then it will be able to map it. But it's trusting that the information in BIM is the most accurate one.
Okay. Yeah, thank you. I just saw Alex post. Yeah, thanks for sharing that paper, Alex. Any other questions from the audience today?
I have a question. I know you mentioned this briefly, but I thought just what are your potential partner profiles that you guys are really hoping for? I know you mentioned it a little bit, but just for the rest of us as we continue to interact with potential, GCs and others, it would be great to know.
Yeah, that's very good. Thank you, Angie, for asking this question. Yeah, indeed. So as I mentioned, we are a research center. So we are not really developing final products. So we really need to team up with someone that is able to take over our research and transform it into a product. And we also like to team up with, this already Hriday mentioned, with use case and users, so we can really develop our solution based on their needs. So we need these two kinds of end users and technological partners. Of course, also teaming up with other research centers is interesting to cover other aspects that we are not researching. But yeah, the main target partner are technological and end users.
Cool.
I have another question based on Alex's article that he shared. how much did the hardware aspect of Spot or the sensor platform that you needed to, add on to Spot, how much time did you spend on that? What was did you have a specific strategy, or was it just based on kind of like whatever the needs of the research was at the moment? Was there customization there?
No, actually with Spot, we didn't do so much of customization because Spot we saw was quite robust as a platform. So we didn't have to play around too much with the hardware. And we could then focus really on the software side, which is quite beneficial. And this is what we want as researchers, that if the hardware doesn't give us so many problems, we can then really invest our time in doing good research. So Spot was quite good in that case. We have the newer platform like the Unity, which is a bit more custom. Like you need to do many custom things, hardware-wise, software-wise, in order to make it completely functional. But with Spot that we started testing initially was really fast, the development.
Thanks.
Yeah, we don't want to reinvent the wheel. They are doing already very amazing things. So we just take the hardware that they have available, and we are just building on top of it this software application, this robot intelligence that they are missing because they are really not focused on this kind of contributions.
And did you, outside of Spot, I could imagine your platform being used by lots of different mobile robot systems, like wheeled systems, mobile bases, bipedal. Have you had any thoughts there, trialed out any other systems?
I think drones would be our first, because this is one of also the research lines that we have at the group. So drones would be one of the next platforms we would like to explore. Multi-robot between a drone and a legged platform could be quite interesting, since we already are working with multi-robot architectures. So now this permits us also to then use not only the same robotic platforms, but heterogeneous robotic platforms like a drone and a legged robot, exploiting the potential of the best of both the hardwares, I would say. So that would be, I think, let's say the most immediate step. Another would be like wheeled robots, if we also find like more like funding or a partner also willing to invest in this direction as well. That would also,
Indeed, we have applied for some funding to work with a wheel leg, so a robot with legs and also wheel.
Cool. Thanks. All right. Any other questions from the audience today? Okay, cool. Well, Jose Luis, Hriday, thank you so much. This was really interesting, and your work is, really impressive. So, it's just a treat to be able to hear more. And Pan, thanks for joining as well to introduce and sponsor this talk. And have a great day, everyone.
Thank you.
For you. Have a great
thank
day.
you for
Bye. Thanks, everyone.
Bye.